Hi everyone, I am Shiva. I am a Ph.D. student from CIPHR Group, Institute of Physics, University of Tartu, Estonia. Our research group focuses on developing advanced computational imaging technologies that consist of new imaging concepts, computational algorithms, and deep learning methods. In this video, I will present about our recent research project on incoherent holography. Fresnel Incoherent correlation holography, abbreviated as FINCH, is one of the widely used super-resolution incoherent digital holography techniques. FINCH was invented by Professor Joseph Rosen from Ben Gurion University of the Negev and Professor Gary Brooker from Johns Hopkins University in 2007. The invention of FINCH had a huge impact in the area of incoherent holography, as it is a motionless technique without scanning with a simple optical configuration and can exhibit a resolution of 1.5 times that of a lens-based direct incoherent imaging system with the same numerical aperture. The first version of FINCH, developed in 2007, was far from perfect. However, FINCH evolved rapidly into the most advanced incoherent imaging method with contribution from many researchers around the world, in addition to the contributions of the main inventors. To begin with, let me discuss the optical configuration of FINCH and compare two extreme multiplexing approaches of FINCH, namely spatial multiplexing and polarization multiplexing. The FINCH, published in 2007, used spatial multiplexing. Light from an object point is polarized along the active axis of the SLM. On the SLM, a spatially randomly multiplexed face mask is displayed. A binary random matrix is used to multiplex two Fresnel zone lenses with different focal distances. Therefore, at the SLM, two object waves generated which are interfered to create an object hologram. As this, in an inline holographic system, at least 3 camera shots are needed to remove the twin image and bias terms. So, 3 spatially multiplexed face masks with phase shift were generated and 3 holograms are recorded, combined into a single complex hologram. The reconstruction result seems to be noisy. Spatial multiplexing, the light from an object is polarized at 45 degrees along the active axis of the SLM. So, only 50% of the light is modulated and the remaining part is unmodulated. A second polarizer at 45 degrees along the active axis is used to obtain the interference. 3 face masks with phase shifts are used to record 3 holograms. The amplitude and phase of the complex hologram are shown here. The intersected result has a higher SNR than spatial multiplexing method, but the light throughput of polarization multiplexing is only 50% of random multiplexing. In our research work, we developed a novel spatial multiplexing method based on a well-known Gerchberg-Saxton algorithm. Our new approach is shown here. When 2 pure phase functions are added, the result is a complex function. Using a complex optical modulator is nearly impossible in an experiment or extremely difficult to say the least. Our goal is to transfer the amplitude part of the complex function into the phase part using GSA. We call it as a transport of amplitude into phase, TAP-GSA. The new GSA uses a Fresnel transform to ping-pong between the mask plane and the sensor plane. The amplitude and phase generated by the imaginary complex modulator at the sensor plane is calculated and used for applying constraints in the GSA. The GSA begins at the mask plane with a pure phase, which is the phase of the imaginary complex modulator. At the sensor plane, the amplitude constraint is applied to all pixels, while the phase constraint is applied to the limited region. This is the compromise I was talking about. The amount of compromise is given by the degrees of freedom, which is compromised pixels by total number of pixels. This is iterated many times until a good convergence is obtained. Face masks for FINCH were generated using TAP-GSA, and the light throughput improved significantly by 150% and 200% with respect to random multiplexing and polarization multiplexing. The SNR of our method was higher than random multiplexing but slightly lower than polarization multiplexing. One unexpected finding in our research is the lossy nature of random multiplexing. One would assume that since only one polarizer is used in random multiplexing case, the light throughput is better. Random multiplexing causes severe loss of intensity. To verify this aspect, we manufactured multiplexed elements using lithography. The diffraction patterns are shown here. Our work has been published now in scientific reports. To thank our team members, Professor Vijay Kumar Anand, Professor Joseph Rosen, Professor Ailatam, Professor Kaupo Kukli, Tauno, Professor Ravi Kumar, Arvind Simon and Andre Blehu for their valuable contributions. If you are interested to know more about our research work, you can reach me through my email ID.